Okay, so our new lecture will be on the gauge transformation. So in the last video, we have discussed that we can represent the electric field and magnetic field in electrodynamics in terms of scalar and vector potential. So in electrodynamics, the electric field can be written as minus del V minus dou I by dou T, and magnetic field is del cross A. So instead of the electric field and magnetic field, we can still use the potentials. There's a scalar potential and vector potential. So it is no need to always use the electric field magnetic field directly. We can also discuss the physics or electrodynamics in terms of the scalar potential and the vector potential, because it is always possible to move from the one formalism to the other formalism. So usually the potential formalism would be easier compared to and the vector formula compared to the field formulation. The reason is if you look at the potential formulation, we have only one vector and one scalar. But in case of the field formulation, both things are vectors. So dealing with vectors is slightly difficult rather than dealing with scalar quantities. So here at least we have one quantity is scalar. So therefore the potential formulation would be comparatively easier. Now the question is for a particular electric field and magnetic field, whether the potential V and A is unique or not. So that means is will be only one possible set of V and A for a particular electric field and magnetic field. So this is one question. Okay, so whether the set VA is unique for a particular electric and magnetic field. Now the answer is no, it is not unique. We can find any number of or any set of the scalar and vector potential which produces or which gives the same electric field and magnetic field. It is, if you look at this expression, we have V and A. Okay, so we can have another V and A which gives the same electric field and magnetic field. So how that is possible? So for that, let us suppose we have two potential VA and another set V prime A prime, which produces same electric field and magnetic field, or produces or represents same E and B. So then, so obviously this B is del cross A, and del cross A prime should also be equal to B. Then B, which is del cross A, that must also be equal to del cross A prime. So how that is possible? Then what is the connection between A and A prime? Okay, so let us suppose is A prime is A plus some quantity. Okay, let us keep it is alpha. Okay, now this del cross A must be equal to del cross A prime. So therefore, okay, let us take this to the next page. Sorry. Okay, so then what would be del cross A prime? So if you take the curl for this particular equation, del cross A prime would be equal to del cross A plus del cross alpha. So alpha must be a vector, del cross alpha. Now del cross A and del cross A prime must be same. So this, okay, this must be equal to del cross A. Therefore, del cross alpha must be 0. So this says that this alpha must be gradient of some scalar quantity. Okay. So we know that the curl of gradient is always 0. The curl of gradient is 0. The curl of gradient is 0. Is del cross delta of some function. The gradient of some function is always 0. So del cross del lambda is always 0. So hence, since del cross alpha is 0, we can write vector alpha is gradient of some scalar function. So this lambda is some scalar field or scalar function. The more correct word is scalar field. So alpha is delta lambda. So hence we have got A prime. A prime is equal to A plus del lambda. Okay. So if you take two vectors A and A prime, if their connection is through this equation, A prime is A plus the gradient of lambda, then both A and A prime would give the same magnetic field. Then the question is, what about the electric field? Should also give the same electric field. Okay. Now the electric field, for if the potential is V and A, electric field we can write as minus del V minus dou I by dou T. Now this must also be equal to minus del V prime minus dou A prime by dou T. Okay. Now earlier we have written A prime is A plus alpha. Okay. Now we have got A prime is A plus del lambda. Now what would be the connection between V and V prime? So we can write V prime is okay, for the time being we can write V prime is V plus beta. So then we can write is equal to minus del V prime minus del B minus dou A by dou T minus dou by dou T of del lambda. Okay. Okay. So sorry, there is one small correction required here. Okay. So what I have done is I have substituted V prime is V plus beta and A prime is A plus delta lambda in this particular step. So we can write minus del V prime as minus del V minus del beta, and minus dou A prime by dou T is minus dou A by dou T minus dou by dou T of del lambda. Now what should happen is, so this must be equal to minus del V minus dou A by dou T. So this implies minus del B minus del of dou lambda by dou T must be equal to 0. Okay. Is it okay? Because if you look at this equation is minus del V minus dou I by dou T, and here we are getting minus del V and minus dou I by dou T. So minus del V and minus dou I by dou T will cancel, and the remaining thing should be minus del B minus, since del and dou by dou T are commuting, we can write minus del of dou lambda by dou T. That must be 0, and that gives, that implies this beta must be equal to minus dou lambda by dou T. Or finally, we'll get V prime is equal to V minus dou lambda by dou T. Okay, so then what is the conclusion? So if we have two set of potential, VA and V prime A prime, and if they are connected through this kind of expressions or in this particular way, then both potential will give the same electric field and magnetic field. Okay. So if AV and A prime V prime are connected, like, sorry, A prime equal to A plus del lambda and V prime equal to V minus dou lambda by dou t. Then both set of potentials will give same electric and magnetic fields. Okay, now this transformation, so this is a transformation from one set of potential to another set of potential. So this transformation is called the gauge transformation. So then how will you explain gauge transformation? So gauge transformation is transformation of potential from one set to the other uh, without any change in the electric field and magnetic field. So the gauge transformation is trying to find uh, another set of potential for the same field. Okay, so basically what is measurable is field. The potentials are not directly observable. Only the observable quantities are the electric field and magnetic field, or its effects are directly observable. The electric field can make the electric force, and the magnetic field also produce the magnetic force. So those things are directly observable, not the potentials. So we always have a freedom on the potentials. We can choose, we can move from a difficult potential to a simpler potential by using gauge transformation. So only thing we have to remember is when you're moving from one potential to another potential, it should be through the gauge transformation so that the field doesn't change. Okay, so this kind of freedom is called the gauge freedom, and the transformation is called the gauge transformation. Okay, so I think it is very clear to you. So in the case of potentials, the potentials are not directly observable. For the same field, we can have infinite set of potentials. Okay, but there is some connection between them. When you're going from one set to the another set, we have to transform through the gauge transformation, and that ensures the field doesn't change when you are changing the potentials. So and its advantages, the certain potentials will be very easy to use. Okay, so if you transform from one set of potential to another set of potential, it will be very easy to handle, and all the calculation makes simple, and finally you can find the field from that simple potentials. Okay, so thanks for watching this video. So in the next class, what we'll do is we'll try to write down the Maxwell's equations in terms of potential. Okay, so thanks for watching. We'll see you in the next class. Bye.